All right, so we were thinking in the last video about ways to undo a derivative, and in particular we were thinking about the fact that, hey, anytime you take a derivative, you're going to get something that results, and that something that results would have an antiderivative. Well, in particular, the antiderivative would be the function that you started with before you took that derivative. And one of the rules that we encountered whenever we were dealing with derivatives was the chain rule, which is to say that if you have a function inside a function, then whenever you produce the derivative, you get first a copy of the original function derivative on the outside with the inside function unaltered, and then a copy of the derivative of what's inside. In some sense, what you can sort of tune your eyes to is that every one of the derivatives that is produced by the chain rule has some piece of the function and some other piece of the function that are related by way of derivative. Because whenever you think of what happens with the chain rule, you're going to have some part of your function, u, and some other part of your function, which is the derivative of that, u prime. Namely, whatever was your inside function is still going to be the same after applying the chain rule, because the first step of the chain rule is taking the derivative of the outer function, leaving the inside function unaltered. And then the second aspect of this is then taking the derivative of the inside function. Well, okay, the long story short there is the inside function and the inside function's derivative are both in the expression of what results in the chain rule multiplied together. So in each case down below, there's a piece of a function and its derivative multiplied within every chain rule derivative. Because when you look at the cosine x squared and the 2x, what results from the chain rule? Within the expression of what resulted from taking that derivative, you've got a piece of the function and its derivative that are multiplied as a result of the chain rule. A piece of a function, 5x plus 2, and its derivative. A piece of a function, tangent x, and its derivative. So now here's what I want us to imagine. I want us to imagine that we are being given this problem, which, by the way, we know how it plays out. We know from what we've already computed that this function results from the derivative of sine x squared. So, well, in particular, the antiderivative of this function would be sine x squared plus c. We know already that the end result is going to be sine x squared plus c. But here's the point. I want us to imagine for a minute that we haven't gone through the process of taking this derivative. I want us to imagine that we didn't already know how the story ended. The question would be, if we hadn't gone through the act of taking this derivative, is there any way that we could look at this function and note anything about the function that would allow us to then compute the antiderivative off of merely recognizing some aspect of this function that would be an artifact of the chain rule? And I claim there is, because you see, what we observed was every time you encounter a chain rule derivative, you have a piece and another piece which are related by way of derivative within your function that would result from that computation. The x squared and the 2x, the 5x plus 2 and the 5, the tangent x and the secant squared. So if you looked at this without having done any of the analysis that we've done to this point, you could see, when looking at this, you're like, this is interesting, because whenever I look at this function, there's a piece of this function and another piece of that function which are related by way of derivative. And now, if we think back to the chain rule, the piece which was of the two pieces, I mean, one of them was sort of the original piece, and the other is the derivative piece. One of them was our inside function, and the other was the derivative of your inside function. Well, your inside function was your u, right? So here's what we're going to do. We're going to set u among these two bits that are within our function that are related by derivative, one of them is going to be u and one of them is going to be u prime. We're going to set u equal to the x squared. And then here's the deal. Think about this. Since u is equal to x squared, we can now say that du, take the derivative of both sides using our implicit derivative techniques, u becomes du, x squared becomes 2x dx. And now check it out. We've got these statements of equality as soon as you set u equal to x squared. And this was a choice because we observed that there were two bits of our function that were related by way of derivative. And we set u equal to the one which would have been our inside function, and u prime would be then the 2x. Well, at this stage of the game, okay, we've got our u equal to x squared. Now, once we've set the u equal to x squared, what du is comes as a result, because you take the derivative of u is du, derivative of x squared is 2x. But what's ultimately going to happen here? Now you have two statements of equality. You can interchange one for the other without disrupting equality. So let's just say what this is here. In terms of u, cosine x squared is cosine u. And in terms of u, 2x dx is equal to du. This derivative, or excuse me, this antiderivative is now totally there for the taking. This is just cosine to a letter. We've, in effect, phrased our original function in a form that is chain rule friendly. And what now? Well, the antiderivative of this is going to be what function has a derivative of cosine u? Well, that's going to be sine u plus c. In general, the function which would have the derivative, specifically, you know the function which has a derivative of cosine, that's sine, but in general, you know that any constant could be added on to the end, and the constant would drop off whenever you would take the derivative to get back to the cosine. But now here's the thing, why don't we circle this answer? Well, we don't circle this answer because the original problem was phrased in terms of x. So we've converted the problem from x to u in order to make it more simple to express. We now can take the derivative with respect to u because we've got the function in terms of u and the du next to it. But now what do we have to do? Well, now we have to get the thing back in terms of x. But you know how to do that because you know that u is equal to x squared. So if you let u equal x squared, well, then we've got it. And actually, this took less space than we even had here on the board to apply to it. So the key was, even if we hadn't done what we did previously to know that the result was going to be sine x squared, when you look at the example, you can see within the function two bits of the function related by way of derivative. One of those is going to be u, one of those is going to be u prime. Set u equal to the one which would then have the u prime also showing up, and then play a little bit of calculus, do a little bit of algebra, and hey, the answer pops up.